So, welcome to another chemistry unit. This unit, as you guys know, is going to move on from phase changes to something called gas laws. And we're going to start that today by talking about the behavior of a gas. So, first of all, there are two or three things, really three, that affect the behavior of a gas. One of them is how many particles do you have present? Okay, how many pieces, how many atoms, how many molecules? The second one is going to be the volume, all right, what size is your container? And then the third one is going to be the temperature. So today what we're going to look at how all three of these things really affect the behavior of a gas. But let's go back to another question. What in the world am I talking about when I say the behavior of a gas? Clearly they're not good or bad. So you know we've got to be talking about something else. Generally when we talk about gas behavior, we are talking about pressure. That's really what we're getting to. So then the next question is, okay, great, but what pressure, what is that? If you think about it, you know this word, you've heard this word, but what is it? The best definition I can give you for pressure is to think about it as collisions between the molecules, and then of course between the molecules and the container they're in. So think about pressure as the number of collisions. The more collisions you have, the greater pressure you have. If you kind of keep that in the back of your mind as we go, this will be much, much simpler. So let's get into our different factors and talk about how they affect gas behavior. And we're going to start with number of particles. So with the number of particles, we're going to do one variable at a time. So we have to make a very big assumption. We have to assume that we are keeping our volume and temperature constant. And from here on out, you'll see V is volume, capital T is temperature. So let's talk about what happens if I increase the number of particles. So a little bit of common sense on this. Pretend these two boxes in my amazing drawing skills are the same size. Whatever, just go with it. So in this one, I have a few gas molecules. Okay, they're bumping around. Actually, picture the gas molecules as members of your class. I blindfold you, take all the furniture out of the room, and tell you guys to walk. So you're walking every which way, you're walking around, you're walking this way, oh, you bumped into the wall. You're going to have a certain number of collisions. But now what I want you to think about is what's going to happen if instead of just your class, I put the entire junior class, all of you, in my classroom. Okay, and I'm so not drawing all these dots. So pretend like the entire junior class is now into your classroom. What do you think is going to happen to the number of collisions? Yeah, a little bit of common sense here. If I increase the number of particles, then obviously you're going to have an increased number of collisions. Okay, there's clearly going to be running into each other more. It's going to be madness. There's going to be fist fights. It's just going to be ugly. And that is an increase in pressure. So by putting more particles into something, assuming you are keeping the volume the same, you jack up the pressure. So if I had a tank, for example, and this isn't one that's on your PowerPoint, if I have this nice little cylindrical tank, you know you're impressed, and then I have my little bike pump over here, now you're going to not be impressed because we all know how well I draw. And it's got a little tank right there. Okay, just go with it. And then the little part sticking out, and then the handle. There we go. If this was at 1 ATM, ATM stands for atmospheres of pressure, and I go ahead and pump twice as many molecules into that tank, what's going to happen? I'm going to double the pressure. So sort of common sense. On the flip side of things, let's say this time I'm going to decrease the number of particles. So we're back to my classroom again. Okay, we have your whole class walking around blindfolded. There we are. We're bumping into each other. And now I get rid of all the girls. Okay, so all I have left is the boys rolling around. What's going to happen? Obviously, if I decrease the particles, that means I'm going to decrease the collisions. And if I decrease the collisions, that's a drop in pressure. So what we see with number of particles is there is what we call a direct relationship. A direct relationship is where one goes up, the other goes up. One goes down, the other goes down. So you see this with changing the number of particles. Okay? Now one thing I do want to mention about decreasing the number of particles, let me go back to my tank example again. Okay, so here's my nice little cylindrical tank, okay, and here's my little valve. Let's say I open up this valve and I let the air come out. Okay? So what I want you to think of is all of the air going to come out of this tank, leaving to no gas molecules left inside? Are they all going to be gone? And you're thinking to yourself, no, that doesn't make sense. what's going to happen is they're going to come out until we get equilibrium. Okay, equilibrium means the pressure outside is going to be equal to the pressure inside. So that's just another little thing to think about. All right, so let's go to the next factor. The next factor we're going to talk about is volume. Okay, volume is the size of our container. So again, we want to do one variable at a time. Let's assume we are keeping constant the number of particles, okay, and we're keeping constant the temperature. Because looking at more than one variable at a time, it just makes life a little bit difficult. So we'll go back to my classroom again. Here's my classroom, all right? Here's all you guys wandering around. So let's start by what happens if I drop the volume. Instead of you guys walking around my classroom blindfolded, bumping into each other, bumping into the walls, let's say I take you and I put all of you in my closet. What's going to happen? Oh yes, we are going to have a big old increase in collisions. Same number of you, but now you have less space to move. So what we see is that if we drop the volume, I'm actually going to have more collisions. And more collisions, as we know, means an increase in pressure. On the flip side, okay, if I take, and well, once again, here's all you guys in the room, walking around, doing your thing, and then I'm going to take you and I'm going to take you all the way down to the gym and put you in there. What's going to happen? Well, again, this is pretty obvious. What's going to happen is, if I increase that volume, you have more room to move. And if you have more room to move, you've got less collisions, and therefore you get a drop in pressure. So this is assuming temperature and number of particles is kept constant. That is a very, very big thing to remember, one variable at a time. But when we look at this, this is what we call an inverse relationship. The direct relationship is one goes up, the other goes up. So the inverse relationship means as one goes up, the other goes down. Okay? Easy. So now let's look at the third factor. The third factor we're going to look at is temperature. And once again, we want to make sure that we are looking at one variable at a time just to understand gas behavior. We'll put them together in tomorrow's lecture. So we're going to assume the volume and number of particles are going to stay exactly the same. Nothing's going to change. So if I have my nice little box here, and you guys can think about it as you walking around the room if you want, and I increase the temperature. Okay, if I jack up the temperature of the floor so the floor is crazy hot, what are you going to do? I know what you're going to do. You're going to move faster. Okay, if I increase the temperature, what I'm essentially doing is adding more kinetic energy. I am making the particles move faster. And if the particles move faster, if I tell you you no longer can walk around the room, now you have to run around the room, what's going to happen is obviously you are going to have more collisions and you're going to have more pressure. On the flip side, okay, if I drop the temperature, I'm actually taking away that energy. I'm taking away that kinetic energy. So I'm telling you, you have to go in slow motion now, like, oh, slow motion. That drop in temp, okay, that slower movement is going to mean you're going to have less collisions, and less collisions we know means less pressure. So again, when we think direct or inverse relationship, what is this? Well, drop in temperature is a drop in pressure. Raise in temperature is a raise in pressure. This is another direct relationship. So when you're looking at the basics here, okay, what you see is you see how different things can affect gas behavior. So now let me throw one monkey wrench at you. What if, instead of me holding everything the same and altering my pressure, what if I hold my pressure the same? Okay, if I hold my pressure the same, believe it or not, temperature and volume will also affect each other. Now we're going to assume the number of particles is the same as well. So if I do that, if I keep my pressure the same, believe it or not, increasing the temperature will actually increase the volume. I want you to think about your bike tires. You put them in the shed, okay? If it gets hot, they're nice and full and swollen. But when you take them back out after the winter, that drop in temperature means you've had a drop in volume. There's no leak in your tire, okay? But their actual ability to fill up that tire is what's changing. Okay, your atmospheric pressure is not changing. The pressure on the tire is not changing. The number of air molecules in your tire is not changing. But you can see this also direct relationship between temperature and volume. So one of the things I always tell people that they can do, and it's a little hard to see this in a video, but I'll just draw it for you, is you can take a piece of paper or a popsicle stick, and you can put a P on one side, a T in the middle, and a V on the other side. And what you can see is that this thing actually can help you remember what does what. So you would hold constant whichever one wasn't going to change. So for example, let's say I wanted to hold my volume constant. Okay, if I were to actually hold that V and move my popsicle stick to see what would happen to my pressure if my temperature went up, then I would be doing this with my popsicle stick. Okay, PTV. My V never moved, I held him still, but I went ahead and moved my temperature up. Well, I can see by doing that my pressure went up. If I hold my temperature still and I move my pressure up, my volume goes down. It's a much easier thing to see in person, but it's worth a shot. The other thing that we see with basic gas behavior is we see something called Dalton's law of partial pressure. And this is the first law we'll do and the only one we'll do in this video, and then we'll get into more tomorrow. Dalton's law of partial pressure is probably one of the easiest laws there is. Okay, what Dalton's law of partial pressure says is very simply the total pressure in a container is equal to the sum of each gas's pressure. Okay, so the total is equal to the sum of the parts. I know what you're thinking. You're thinking, duh. Okay, but that's literally what we are doing here. We are assuming that this is actually what's going to happen. So if I have a container, here's my tank, and I have, different kinds of gases in there. Okay, so here's all my different gases that I got floating around in there. And if I tell you the pressure of the red one is 3 atm, and if I tell you the pressure of the blue one is 2 atm, and I tell you the pressure of the green one is 1 atm, and I want to know the total pressure in the container, literally Dalton's law says add those numbers, the total pressure is 6. That is actually one of the laws. Now, the cool thing about Dalton's law is it means that we can treat these little gases, the greens, the reds, the blues, as if they don't affect each other. The fact is, they do affect each other, and we'll get into that more tomorrow, but we're just going to assume that they don't. We actually can look at them separately, which makes our life easier. So, with Dalton's law, sometimes you will see different pressure units. In fact, with all of our gas laws, you will see different pressure units. There's a ton out there. In chemistry, we mainly use 3 of them. Okay, we use KPAs, it stands for kilopascals. We use ATMs, which stands for atmospheres, and we use mmHg, millimeters of mercury. You see that with blood pressure a lot. Normal atmospheric pressure is 1 atm. You need to know that. Okay, it also is 101.3 kPas. You do not have to memorize that. It is also 760 millimeters of mercury. You don't have to memorize that. Sometimes you'll hear torr, sometimes you hear PSI. There are all sorts of different ways to measure pressure, but these are the big 3 we use, and this is normal atmospheric pressure. So tomorrow we'll come back, we'll talk about some more gas laws, and go from there.